Last 2 weeks, we've mainly focused on the adele space and the Weil differentials in order to be able to complete the proof of the Riemann-Roch theorem. And now, with another motivation and our motivation in the coding theory, we want to understand the local components of these Weil differentials. And our main purpose will be to understand another description of the algebraic geometric codes, or the orthogonal component, or the dual of the algebraic geometric codes, as we have considered, like evaluation codes. So for this purpose, so to be able to understand the local components of the Weil differentials, we need to introduce another local embedding rather than the principal adeles. In this case, we consider an adele. Let me denote it by iota. This is an adele, which is defined as a kind of, again, sequence, but it is defined with respect to fixed p. So that means at the pth component, we are going to have a function from the function field, and the other components will be assigned at 0. And obviously this is an adele, because we can see that for finitely many places, or for almost all places p, its all components lies in OP, or equivalently for finitely many, this E of p lies in OP, or equivalently for finitely many places VP of x, it's really, and because VP of 0 is going to be infinite, so it's enough to check VP of 0 and VP of x, and this can be negative. It can be also positive, but it can be negative for only one place. So this is finite many, and this shows us this is an adele. And in general, we can also see that for any adele, we can represent it as a sum of this, let me call them like local adeles, even though it is not, there is no such keyword in the literature, but by the local adele, what I want to mean this special adele we consider here. And in other words, if you consider the definition how it is given in the textbook, for a fixed place p, for a function f, iota p of x is an adele whose pth component is x and all others are 0. And indeed, by using this spatial adele for a given Weil differential, its local component is defined as course, local component at this given place P is a k-linear map from the function field to the k, and this k-linear map explicitly described as the Weil differential, the image of this local adele under the Weil differential omega. And this is obviously k-linear because we know that any Weil differential is k-linear, and by the definition of its local component of this Weil differential at place P, we can verify that Vp also, omega P is also k-linear map. So first, we want to understand that these local components are not identically 0. And along this way, first we need a proposition which tells us for a given Weil differential omega and an adele alpha, the local component of the Weil differential is not zero for at most finite places. So that means for almost all places, Vp of alpha p is going to be 0. And moreover, we can compute the Weil differential of an adele by, in terms of its local components. And in particular, if we replace the adele alpha by the principal adele whose components are determined by only one, this is the multiplicative identity of the constant field, what we get is that the local components of this one, sum of these local components one, is going to be 0. So indeed, we will often use this statement, but this statement is also known, a kind of algebraic version of the residue theorem on the compact Riemann surfaces, which is explained with compact surfaces. And to understand, actually, we are not going to mention this relation deeply, but the first step can be to understand the chapter 4, how these indeed Weil differentials are also related to the derivative of some functions, and how we can get this statement and how we can view this statement as an analog of the residue theorem in the complex, like in the complex analysis or on the compact Riemann surfaces. But for the moment, we only want to understand how it works by the definitions in an algebraic way. And in general, we can suppose that omega is a non-zero differential, otherwise everything is going to be 0. So that means Weil differential is not identically 0. And we can consider its divisor, who is going to be canonical divisor. And first we want to note that there exists a finite set of places such that whenever consider place outside of this collection, we get the valuation of omega. So the coefficients of the divisor omega at place P is going to be 0, and Vp of alpha P is positive. So actually, such a set exists because if omega is a divisor, we know that for finitely many places we have non-zero coefficients at the place P. And on the other hand, since alpha is an adele, we know that Vp of alpha P is positive for almost places P, or equivalently, we know that for finitely many places P, we have VP of alpha P negative. So indeed, this finite set can be considered as the intersection of this finite collection of these places that gives us these properties. So such a finite set exists. And now, depending on this set, we want to consider an adele where we define at the pth component we assign alpha p, the pth component of the adele we fix in the statement. Whenever this place does not belong to this finite set, otherwise we are going to set 0 where the pth component, where the p is element in S. So first thing we can see is that beta is an adele in the adele space of the canonical divisor omega, because for P in S, by its definition, VP of beta, VP of 0 is going to be infinity, and this is always bigger than or equal to VP of W, whatever it has positive or negative integer. And when P does not belong to S, by the definition, we know that VP of alpha P, VP of beta P is going to be determined by the VP of alpha P. And for this, in this case, by our assumption, we know that VP of alpha P is always positive, which is equal to VP of W as well. So that means this adele we introduce here is an adele in the adele space of the canonical divisor. So that's good. The other thing we can observe, if we set such an adele, if we consider such an adele, we know that another adele alpha, not another adele, but for any adele we consider can be written as a sum of the adele beta and the local adeles, which are determined by the iota p of alpha p whenever p in S. By the definition of beta p, we can obviously verify that. So if we take the Weil differential of this adele, and since a Weil differential is k-linear, we can see that the Weil differential of alpha is Weil differential of beta plus Weil differential of sum of iota p of alpha p. And since, as we have seen, that this beta belongs to the adele space of its divisor, the divisor of this Weil differential, we can see that this quantity is nothing but 0, because beta is an adele in this Weil differential. So that means we also know that omega vanishes on A of W plus F. So if this vanishes on this space, it also vanishes on the adele space of the canonical divisor. So this is why we have 0. And again, by the linearity, k-linearity of the Weil differential, indeed we can write this equality in terms of the local components of Weil differentials at given places P. This is just by the definition of the local component of a Weil differential. So here the thing we need to observe that, okay, for P in S, for this finitely many set, we have such an equality, but what happens when we consider the places outside of this finite set? Because we also want to see that for finitely many places we have non-zero quantity. So that means if we consider places, this finite set connection, finite set of collection of places, that means VP of alpha P is going to be 0. This is the thing we want to see here. So when P is outside of P, E to P of alpha P is belong to the adele space of the canonical divisor, because we can easily verify that VP of alpha P is bigger than or equal to 0, which is nothing but minus VP of P, thanks to our setting. And if these local components belongs to the E to P, their images under the Weil differential is going to be again 0. And in this case, Weil differential of this local adeles, by the definition, that means the local components of the Weil differentials at place P are going to be 0. And in this equation, if we consider the principal adele, whose components are the multiplicative identity of the constant field. And since we know that the Weil differential vanishes on the adele space of the canonical divisor plus F, it's also particularly vanishes on the function field. So indeed it is 0. And this shows us the first equality. And the second, the right hand of the this identity, this equation, is determined by this equality. So, indeed, this completes the proof. And now the question is that, okay, if we, so what we have, do we have the local components as 0? Because we also want to see that these are non-zero quantities. And moreover, in general context, we can see that Weil differentials are uniquely determined by their local components, as we will see in proposition 1.7.3.